Hi everyone, it's me, Carolyn again. And in this video, we're going to start doing some inferential types of statistics. And you can remember there are two major branches of statistics. One is just descriptive, where we just describe the situation. Inferential is when we start looking at data and we start inferring something about that. And this piece here is where we kind of start getting our little bit of a taste of what that would be. So first of all, what we're going to be looking for is usually like the average of something. We can do this for other variables as well, but we're going to be looking at finding like the average of a population, the mean of a population. However, we won't be able to go out and actually calculate that because we just don't have the time, we don't have the resources, we can't get to everybody in this whole population. So a lot of times we use a sample to kind of get a guess. And so that's what this kind of talks about. So a point estimate is a sample statistic. So something that we're going to calculate on our sample, we'll call it a statistic, that we use to estimate that population parameter. Now, in most of the time in this class, what we're going to be doing is finding one for our mean. We'll do it for another parameter a little bit later, but you can do this for a lot of different types of parameters. So if we were just trying to think about what a good estimate for, and this should be what do you think would be a good estimate for the population mean would be, and I think that you guys would eventually come up with the fact that the sample mean might be a good estimate because we're taking some things, adding them together, and we divide by however many we have. And that is exactly what we do use for our point estimate. This is considered to be an unbiased estimator because they have the same average. So the mean of our X bars is equal to the mean of the population. We got that from the previous video. And we also had some other things about the shape. It was also normal and under certain situations, and we could also find the standard error. However, we know that if we do take a sample, that sample is not completely accurate. There's probably some error between the actual value and our estimate. So the estimation of error, so is the absolute value. We like to think error, not too much about being bigger or smaller, but that there's some error going on there. And that error can be found out, it turns out, and again, we aren't going to be finding the reasoning behind this. We're just going to be learning how to use this. And what we do have, if we have X bar and it follows our normal curve, that we can have the margin of error being this critical value. We'll talk more about that in a moment. The sigma, which is our standard deviation of our population, and divided by the square root of our n. And n again is our sample size. And m is going to stand for our margin of error. How off are we going to be? This formula that we have does take into consideration some sort of confidence level. The confidence level we're going to use is going to be denoted by C. And when we talk about a confidence interval, it's going to be basically how confident I am in my estimate. Do I want to be 95% confident? So in other words, I'm 95% sure that my value is correct. I'm 99% sure that my value is correct. We designate these critical values. Sometimes we will use a Z star, and I believe we've seen that Z star before, but here's where we really get the idea behind it. Such that the area under our curve, whether that be a Z curve or some other curve, which we'll see later, is going to be given this way. So the area between those two values is that C. So that 95% confidence, that 68% confidence, and so forth. Our text does kind of go through the development of this next, the formula, I'm not going to. We're going to jump right into how do we find those critical values. And I'm going to be using SALT. So we will be using critical values. Again, notice they are a Z. So when we see Z, that should hit to us that we are using the standard normal. And these would be used a lot of times if we were using formulas versus our statistics and our statistical packages that we use. We have SALT, but we're going to use SALT to get these values because I'm also going to show you how we can do some of the work by hand. And then we'll also learn how to do it using SALT. But I'm going to be using SALT to find our 95% critical value, my 90% critical value, the 90% critical value, the 80%, and the 99. So first I'm going to draw pictures, and then we'll go to SALT and actually find them. So what we're going to be doing in SALT is we're going to be looking for two values. Okay, remember this is our standard normal, so it is centered around 0. So we're going to be finding a negative Z star and a Z star, where the area between these two is 95%, or in terms of probabilities, 0.95. Here, we're going to just change the area to being 0.90, so between two values, and they will be symmetric on both sides, although my picture was bad. So we want 0.9 in here, 90% here. Here, I'm going to have 80%, so a little bit less, and I should have been shrinking these a little bit. 0.8 in here, so we're going to be looking for this value and this value. They will be centered around 0, and then 99, that's quite large. Okay. So we want 99% here, so 0.99. We're going to be looking for that value and this value. Before I go there, though, 95%, we should be able to figure out kind of what those values are. Roughly speaking, if you remember the empirical rule, we had 68% within one standard deviation, 95 within two. So that Z star here should be pretty close to the number 2. Okay, we would get 99.7 if we were between 3. So that those two values are going to be kind of close to 3. They are going to be more accurate than the empirical rule, but we're going to use SALT to find that more accurate idea. So bear with me for a little bit while I switch to SALT. And I'm going to be going into my standard normal. So again, mean of 0, standard deviation of 1. We're looking for an area between, so we're going to be using the between button. And I know the probability, so I know this yellow shaded piece. So I'm going to be changing this box down at the end. And I want that to be 0.95. So notice we get a negative 1.96 and a positive 1.96. I just took a moment and wrote that down. Those numbers are pretty darn close to 2. These are actually more accurate because you can remember we also looked at what is the probability between a Z being between -1 and 1, and we didn't get the 68%. We had like 68 point something percent. Okay, we're going to do this also for a 90. So we're going to change our 95 to a 90. Very quick and easy to do. So my Z star is at 1.6449. We can change it to a 0.8, find 80%, our critical value for the 80%, 1.2816. And then we'll also do 99, which I said would be pretty close to a 3. And it's not quite there because 3 was actually 99.7%. So we get 2.5758. So those are our Z stars. So going back to our notes here. Okay, kind of revamp what I just did. So my z-star, this would have been a negative 1.96 to 1.96. Those are like z-scores, a negative 1.6449 to 1.6449. We usually just have the positive value because we will use the plus or minus in our formulas. So these are how you could get them. We could do a whole mess more if we wanted to, but I did put in our notes a nice little table for 80%, 85, 90, 95, 98, and 99. These are probably the most commonly used values. And so I thought I'd just put those in there for your reference. Okay. Let's put this kind of what we've got together. So let's say I have a sample that has a mean of 15. We have a population standard deviation of 2. We had a sample size of 25, so we had 25 people that came in. We added them all together, and we got our sample, and we wanted to be 95% confident. So what is our point estimate? So our point estimate, remembering our point estimate is just simply the X bar. That was our 15. Our margin of error, that would be M. And the formula we had for M, how accurate we wanted to be so we could get that confidence level, is our Z critical multiplied by our sigma over the square root of N. So we have a 95% confidence interval. So we need our Z star for the 95%, which we just found, to be that 1.96. So I went back to the previous table and I pulled off that 95% and got that 1.96, just pulled it right off from there. My standard deviation was given in the situation, so that's my 2 over my square root of 25. This is multiplication going on between these two pieces. So first thing I'm going to do though is my division. So I'm going to take 2 divided by that square root of 25. So 2 divided by 5. And then I'm going to multiply that by 1.96. So I am fairly confident that my point estimate is accurate to 0.784. So I'm 95% sure that my point estimate, that the true mean is somewhere between going up a little bit and down a little bit of that 15%, that 15. So what we do is, since I kind of told you, here's my point estimate, and I am 95% confident that my true mean is within that bar from my point estimate. So we're going to create an interval, and we call this interval a confidence interval because I'm somewhat confident, 95% confident, that my average is from here, some lower end to some upper end. And that upper and lower end will be determined by this margin of error. So I'm kind of skimming down here. So this is kind of how we did that. So we're going to take our statistic, that point estimate, and we're going to add and subtract that critical value and the standard error. So remembering standard error was that sigma over square root of N in the case of X bar. So we get that point estimate plus or minus some margin of errors that I'm pretty sure it's this number, but I'm going to give myself a little cushion to go a little bit smaller and a little bit bigger. And that's going to create what we call a confidence interval. So because we'll have a smaller number and a larger number, an interval from here to here. That confidence level is going to be, is what helps us determine that error. How confident am I going to be using to construct this? If I want to put it in terms of pieces, we're going to have this X bar plus or minus my Z critical, sigma over the square root of N. Okay, let's do in the example from our previous one. So we had our sample to be X bar was 15 plus or minus, and I'll just rewrite the formula first. I'm going to use Z star sigma over the square root of n. This would have been our 15 plus or minus that 1.96, and then 2 over that square root of 25, or 15. We had already gotten that value to be 0.784. There were not other digits associated with that. So then I'm going to get an upper value and a lower value. So I'm going to put my upper one, upper value, or upper boundary if you want to call it that. And my lower one, I'll put that down at the bottom. Or lower value. So the upper is going to be gotten when I do the addition. So 15.784. And then my lower one, if I take 15 and subtract that, I get 14.216. Sometimes we use a little bit of notation to make it easier to read. We'll write this in interval notation. Okay, so I am 95% confident that the true average will fall between 14.216 and 15.784. Okay, could I have gotten salt to do this? You're going to think about that. We're going to do another example by hand, and then we'll use salt to actually get that value. And well, when we're in salt, we'll come back and do this one as well. So let's try another one real quick. So let's say we have a sample mean. I don't know what we're measuring. Doesn't really matter. We have a sample mean to be 20. Our population standard deviation is 6. We had a sample size of 100, and our confidence level again is 95%. So we want to find the confidence interval, so our lower bound and upper bound, for the true population mean. So being 95% confident, then it's going to be in that interval. So the formula again, X bar plus or minus, I'm going to put Z star sigma over that square root of n. My X bar is that 20 plus or minus. We're doing a 95%, so my Z star is still that 1.96. My sigma in this case is 6. My n is 100. So I'm going to do this, add this piece at the end first. So I'm going to take that 6 divided by the 10, multiply that by the 1.96, and I'd have 20 plus or minus 1.176. So my upper bound, adding them, so I can do that without a calculator. I prefer using a calculator to do the lower end, 18.824. So my interval is somewhere there. Now, how could we get salt to help us? Unfortunately, when we have this situation with Z star, there is no calculate the confidence interval or the confidence interval for this situation. I have to do a little bit of work, but it's not too bad. So I want to remind us of the central limit theorem, because X bar, if the original data was normal, which we are assuming, the X bar is also normal. And we also have n more than 30, so we are good here as well. Our X bar, our mu of X bar is going to be the same as it was before. Sigma of X bar is that 6 over the square root of 100, which is 0.6. In the previous one, our sigma for X bar is that 2 over the square root of 25, which is at 0.4. So I can kind of calculate that as well, because we're going to go back and verify these as well. So just be aware of that. So when I'm in there, in salt, I'm going to do both of these questions. Okay, so but I'll start with this one first and then do the previous one as well. So I'm going to go into salt. Okay, and it's going to be similar to how we found our Z stars. But we're going to change what curve we're looking at. We're no longer going to look at our standard normal. We're going to look at the normal that pertains to the X bar that we're looking at. So X bar, the mean there was 20. That was our sample mean. And this had a standard deviation of that 6 divided by the square root of 100, which was 0.6. And we want to find a 95% confidence level. So I'm going to put 95 right in there. And notice there is my lower bound, 18.824, which is exactly what I got with the formula. And the upper bound, 21.176, which is exactly what I had for the upper bound. The previous problem, a little bit different. We had an X bar of 15. And our standard deviation was 0.4, still looking for that 95% confidence level, but there was that 14.216 that we had, and the 15.784 that we had. So we can use salt to help us find these, and we'll practice a little bit more with some other examples. But I have a little bit more to do before we do another example. So let's go back to our notes. I'm on to another page just to kind of clean some things up. Okay, so I kind of want to know what's going to happen if this confidence interval. So let's say the confidence interval, we're only going to change one thing, and we want to increase our confidence from, say, 95% to 99. So I want you to think about what's going to happen to our interval. Is it going to get bigger or is it going to get smaller? Okay, so if we had our interval, remembering our interval kind of represents 95%, and we had a curve up here, and we want to become more confident, so we're going to get more area. So we're going to go from like 95 to 99. We have to go out to get more area. So the confidence interval will increase. Will increase. Okay, now let's just say, starting again, then we have a certain confidence interval, and this time I'm just going to get more people. So we're going to increase our sample size. So say from 10 to 50. And I use that to get my new X bar. But everything else is going to stay the same. So the X bar turned out to be the same in everything. So it's not going to be shifting left or right or anything like that. But the X bar stayed the same, but I had more people. What's going to happen to our interval? Is it going to get smaller or is it going to get bigger? And then why? So we have to think a little bit. So if we gather more people, my estimate should be more accurate. So I should be more confident. So my interval margin of error should be smaller. So it's going to actually get smaller as well. Interval will decrease. Decrease. Okay. And if you think about the formula, okay, if n gets larger and we take a number and divide by a bigger number, this gets smaller because we are more accurate. So our margin of error is going to shrink a little bit less. Okay, let's do a few more examples of finding some confidence levels, just so that we get the feeling for salt. I've got 2 more examples. Actually, I have 3, but we're not going to do the third, but we'll talk about it. Okay, so let's say we have 100 people was given an IQ test. The average IQ score turned out to be 110. We want to find a 90% confidence interval if the standard deviation of the population is 15. So again, we would be, if we wanted to do it by hand, we easily could calculate the pieces. My X bar, that's the sample mean, that's 110. Plus or minus my Z star for 90%. We'd have to remember that is, gotta look it back up again. Don't have these memorized, 1.645. And my sigma was 15, square root of n, and we had 100 people. Okay, but I will need that standard error because I need to put that into SALT. So I get 1.5. Okay, and I'm going to go to SALT and do it instead of using my calculator. So I'm going to go into SALT. Okay, the mean of my distribution is the mean that I got, that average, which was 110. We had a standard error or standard deviation of our X bars to be 1.5. Make sure you do that dividing by the square root of n, because otherwise your interval is going to be way too large. We wanted to find a 90% confidence level, so we have to change the 95% to that 90%. And we get a lower bound of 107.5327 and an upper bound of 112.467. And that's it. So we can go back and get our next example and keep going and do some more fun. Isn't this fun? SALT is such a help. Because not that this formula is difficult. This formula really isn't all that bad. We do need to know what our Z stars is. We don't need to know Z star when we're going to calculate it in SALT. So just realize you don't even need that piece. All you need is the information given in the problem. The Z star is actually built right into the system when you put in that 90% at that end. So there was our lower bound and our upper bound. So I am 90% confident that the true average for this IQ test is somewhere between 107.5 and 112.5, if I'm just rounding to the nearest 10th. Let's do another example. Okay, a national research firm has past data that indicates the interview time for customer opinion survey has a standard deviation of 6 minutes. What is a 95% confidence interval of the average interview time if they took 250 interviews and they resulted in an average of 20 minutes? So my mean, my X bar, which is something I do need, because that's going to be my mean that I'm going to use. I'm going to use 20, so that's my mean that I'm going to be using. And then we're adding and subtracting a little bit, the margin of error, to create our lower bound and our upper bound. SALT will need that standard error. And the standard error is going to be that 6 divided by the square root of 250. I am going to need to get that in decimal form so that I can enter it into SALT. So taking 6 divided by the square root of 250 gives me 0.379473319, which if you were doing it by hand, you'd have to calculate anyway, because you calculate that piece right here, and then you multiply it by the Z star. I don't need the Z star because I will be entering the 95% into SALT, which will then generate the Z star and do all the work in a matter of seconds, which is kind of nice. It does it all for me, but you still have to realize what we're putting in. So we have to put in the mean, which was our 20, that X bar that we calculated. So that's our point estimate. And then we're going to go up a little bit and down a little bit. I should go this way. I don't know, up and down a little bit. And the up and down we go a little bit is that Z star times that standard error. Our standard error was the 0.379. I don't know how many digits we'll put in. 473319. That's how many my calculator gave me. So that's best I can do. And we are looking for a 95% confidence level. So we're going to change that 90 to a 95. And we get 19.2562 up to 20.7438. A lot of times we don't need all the decimals, but I'm going to just write them all down and make sure that we understand how this all works and what this means. So it tells me, and look, that's not very big. Think about it. That's not very big, like 0.75-ish, 0.74. Very small, but that's because we had 250 people. So the larger our sample size, the smaller our interval will be. All right, so I am 95% confident that the time it takes for these interviews is between 19.3 and 20.7. I just wanted, and that would be in minutes. Okay, let's look at another example. Not actually going to do this one, but I do want to talk about it because sometimes when you are doing your homework or doing real life situations, we have raw data. So we have numbers. We don't have what X bar is, what's the standard deviation is, or any of that. So a lot of times this is an example. Parents are kind of concerned, wondering when their kid's going to finally walk. So this is the month at which they started walking. And these are 40 kids. Okay, so this is our data. And assume that the population of standard deviation is 1.9. We wanted to conduct a 90% confidence interval for this true average. Okay, so the first thing I want to remind us is the formula looks like, Z star. The first thing we need is X bar, okay? Which means I would have to calculate it, which means I need to add all these data values up and divide by 40, okay? The nice thing is we do have technology that can do that for us. We could put all this data into a spreadsheet and boom, it would spit out our X bar. I could then use that in here or in SALT to get there, but I do have to go that one extra step. If I'm doing this for my class in homework, if there's raw data, you will also have that SALT button picked out in there as well. And you can just, once you hit that SALT button, all this data goes right into the program. And you can find X bar. It will be located in the descriptive statistics button. Okay, so when you're in there, I'm going to go back to SALT, kind of show you. So when you're in SALT, you're going to want to go back here in this descriptive statistics. I wish there was a way to nicely show this, but you will have some information there that is directly related to this data, and it will have your mean, your standard errors, all that kind of stuff. But you were going to make sure we're using the standard error for this question. So we will make sure to use the standard error, not the one that is given to you in the descriptive statistics. We have to make sure to use this one, which would be 1.9 divided by that square root of 40. That will be the standard deviation that you'll be entering into SALT, not the standard deviation you get from the sample. So just be aware of that. Okay. All right. So that's kind of going to end our discussion on calculating standard or confidence interval. But I do want to go into a little bit more because all of this has required us to know this thing right here, the standard deviation of the population. And sometimes we don't know that, and sometimes we do. But even before that, suppose we wanted to start from scratch and we want to create an interval that has a certain size to it. Like I want to be 95% confident and I want to be within half a centimeter or within 2 minutes or within 5 pounds, whatever we're measuring. So I have this idea of what I want the interval to look like and how accurate I want to feel. So then I want to know, well, how many people do I need to go out and ask in order for that to happen? So we want to find N. Nice thing is we can find N by taking this margin of error formula and solving it for N. So we're going to basically solve it for N algebraically, and it turns out to look something like this. So we'll have that Z star, the sigma, and M. Remembering M stands for the margin of error. How far off are we allowing ourselves to be? And going from there. So let's do a few examples. Unfortunately, salt can't help us with this, but the formula isn't too bad. So note N represents a sample size, like the number of things we have to calculate. That has to be a whole number. To make sure we get what we want, we will always round up. No matter, even if rounding rules tells me to round down, I want to make sure I'm going to get the margin of error that I want and the accuracy that I want, the confidence that I want. So we always, always, always round up when we're talking about sample sizes. And getting one more person to make sure that I get the accuracy and the confidence I wanted is better than not getting that piece that I needed or wanted. Okay, so let's say I have an athletic trainer who wants to determine how large of a sample should be taken to be 99% confident that his true estimate is between true average for healing an ACL tear is to be within 1 week or less. So he wants to make sure that once he gets this average, that if we go in 1 week, either direction, we will be getting that 99% confidence level. And it does show that records of past patients has a standard deviation of 3.55 weeks, which is something we needed. So our formula for N, first of all, let's write this down, is that, kind of get some big pieces here. We have the M on the bottom, we have our Z star and our sigma up there, and everything is squared. Okay, so first thing I need to do is go back to my table and find that Z star for my 99%, and that is 2.576. I pulled that right from the table that we had earlier. My sigma, that is my standard deviation of my population, that's going to be that 3.55. The margin of error, that's how accurate we want it to be within 1 week. And then we're going to square all those things. So I'm going to multiply those two numbers together. So 2.576. And multiply that by 3.55. Going to get that value, divide by 1, which doesn't change anything, and then I square it. And I come up with 83.627 and so more digits. But remembering N is a whole number, and we always, always, always round up. We need 84 people. Now, if I take more, we're going to get more accurate and we can be more confident. Or more confident. We can't have both, or we could have both depending on how we set it up. Okay, so here we go. Another example. Recall the example about interview times. Let's say we didn't know how many people we should go out, but he wants to have a 90% probability, 0.9 probability, which is like 90% accurate, that the true interval is within 2 minutes. We're going to remember that the standard deviation was 6 minutes. So, and you can remember from our problem I can look back real quick. We had that our interview time actually was within 2 minutes. So we're going to probably find an answer that is less than that 100 people that we had before. But let's just verify it too. But I think we were also 95% confident. So here we don't even want to be that confident. So we will get a much smaller number. All right, so it's Z star sigma over their M squared. Z star for 90% is 1.645. Again, I just took that right from the table. Our sigma is that standard deviation, so that is 6. Our M, that's how far we want to be accurate within 2 minutes. So that's our M, and we're squaring all that. So I'm going to do what's inside the parentheses first. So 1.645, and I'm going to multiply that by 6. Divide that number by 2. And then I'm going to square it. And I get 24.35. But we always, 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 always round up. Even though this says we should round down, I'm going to round up. And I get 25. So I only need to get 25 people to make sure that I'm within 2 minutes at 90% confident. And we had, in the problem we did with this example, we had 100 people and being 95% confident, and we were within the 2 minutes. So that is why we have a much smaller N value here. So this concludes the video on kind of this confidence interval idea when we know some information. However, one of the biggest things that we had to know for doing this is this sigma. That was in all of our formulas, sigma and sigma. And sigma represents the population standard deviation. Well, if I don't know my population mean, that's why we're finding X bar to begin with, and we're using it to get a feel for where mu is, why would I know sigma? Come to the next video to find all that out. I hope to see you there. Have a great day.